Okay, so let's work this problem. This one's a little different from some of the other ones we've looked at. You might notice right away that at A I have a single reaction, a vertical reaction, a shear reaction. Over here at C, I would have shear and moment and axial. So it looks like I've got too many unknowns, but you'll notice right here at B there's a hinge. So that means we'll be able to separate these two apart. So before I can do anything, we have to find our reactions. So in this problem, that would include the shear force at B. So what I'm going to do first is draw a free body diagram of the section AB. So I'm going to, it's 4 meters. And on that, I'm going to write that at A, I have a positive shear at A. At B, which is the pin, I'm going to write that I have a positive shear at B. And then, of course, across this section, I have this distributed load. The intensity of the load is constant, so it's a uniform distributed load. It has a value of 5 kilonewtons per meter. And I'm going to find the concentrated equivalent of that to help with my statics. So when you take the area of the curve, it's being a rectangle, the area is just base times height. So that's 4 meters times 5 kilonewtons per meter, so that's 20 kilonewtons. And it would be located 2 meters in from either side. I think that's all that's there. There's no moment at A because it's a pin or a hinged roller, and there's no moment at B because it's an internal hinge also. So I'm going to sum moments at one end and find the other reaction. I think I'll sum moments at B. No particular reason. So I'm going to sum moments at B, make sure it's in equilibrium. I'm going to use right-hand rule. So about B, my applied load creates what kind of moment? Positive or negative? Positive. So I have a force of 20 kilonewtons and a distance or moment arm of 2 meters. Then all the way over here on the right, I've got my shear force, which is going to create negative moment. So I have a force of the shear times a distance of 4. And that's not hard to solve for. You can find the shear at A is equal to, what is that? 10? No. Yeah, 10. Yeah. And it's positive. So I have positive shear at A. And then to finish this off, I can find the shear at B by summing my forces in the y direction, vertical. Make sure they're in equilibrium. I'll assume up is positive. So this shear at A is up. The shear at B is down. The force from the applied load is down. So I should be able to solve for the shear at B. And it looks like it's negative 10. I've got negative shear at A. I'm sorry, positive shear at A, negative shear at B. So far, so good? That's pretty easy. That just looks like a little simple supportive beam with a uniform load, right? So basically the total load, 20 kilonewtons, is distributed equally to both sides. So then we'll come down and do the free body diagram from B to C. And let's draw that little bit. So again, I'm going to assume positive shear at B. On this diagram, I have to assume positive shear at B on this diagram. Equal, right? Equal and opposite. Positive, but they're both positive shears. And then right in the middle, I've got my applied load, which is 8 kilonewtons. That's 1 meter, 1 meter. And then on the free end, on the fixed end, I'm going to assume positive shear and positive bending moment. Now, a quick review of our free body diagram is these are the only two things I don't know. Remember, I already found the shear at B. It was negative 10. So when I write my equations here, wherever I see shear at B, I'm going to plug in negative 10. So you can do anything you want. You can go ahead and find the shear first, sum forces in the Y. You can sum moment, whichever one you like. I'll do the moment equation first. So we'll sum moments about where? Where should I sum moments? You can sum moments at B, but you'll get also C, the shear at C, which I don't know yet. So that's probably not a good place to start. Where else? C. Did you say C?
Yeah.
Oh, I'm sorry, I misunderstood you. Yeah, C is the best spot. So we're going to sum moments at C, again using right-hand rule. So with my right-hand rule, this is a positive moment. About C, my 8 kilonewton force creates what? Positive or negative moment? Positive. So I have a force of 8 kilonewtons. What's the moment arm? 1 meter. And then the way I've drawn my shear here, what kind of moment does that shear create about C? Positive or negative? Negative. And has a moment arm of 2. So we can solve for the moment at C. The moment at C. Remember, this value for 10 goes right in there. It is negative, so that negative will cancel that and make that a positive. So this becomes positive 20, and this is positive 8. That's 28, so the moment must be 28. Is it positive or negative? I believe it is negative. So that's 28 kilonewton meters. Now I could have done this equation first if I wanted to, but we'll do it now. So we can sum forces now in the Y direction, vertically.
Would it make no difference?
No, because we already knew shear at B, so I could have no, it won't make any difference. Now what would make a difference in this calculation is if you mishandled the value for shear at B, well then you're going to miss all these too, because we're having to bring that information from B down and use it again. And it's going to even show up here. When I sum forces in the Y direction with up being my sign convention, well I've got the shear at B up and the shear at C down. So it just says the shear at C is equal to the shear at B. So the shear at C is equal to the shear at B, and the shear at B is minus 10, so this is minus 10. Oh, thank you very much. So that's minus 8 kilonewtons. So that's not true anymore. So it'll be 2, what will it be? Let's see, shear at B is minus 10, minus 8 is minus, it's going to be 18, right? Well, that's interesting because I can just do this. See, I never made a mistake. So when you look at the PDF of this, it'll look like I was a genius. If you have nothing else to do and you watch the video of us talking right now, you'll see that I was a complete idiot. So you choose which one you like to view me as, genius or idiot. I have a feeling the second is more likely the case than the first. All right, so we've got all of our bits and pieces, we're ready to roll. So let's draw a template. I'll start with the left side and we'll go to the right side. Oops, is there anything that we know? Well, the load's going to transition here, so that's probably a good point to add to our template. Plus, what's unique about B in the moment diagram? What should the moment at B, what should that be equal to? Should be 0. And then we've got this force here transitioning left to right. That's going to be a change, so I need to add that to my template also. So that should be enough to get me going. So let's come back and assume a positive x-axis and a positive axis for our shear. and all these numbers will have the units of kilonewtons. So starting with our shear at A, what is the shear at A? When we solved for it, it was 10. So I will put that as positive 10. Hey, we also know the shear at B. What's the shear at B? Negative 10. So I probably should come in here and mark that. What's the shear at A? I'm sorry, shear at C? Minus 18. I could mark that. So these are values that I've already computed. I better hope my shear diagram matches that. So let me draw a little line here so that we can have a kind of a break. So remember that the change in shear between any 2 points is the area under the load curve. So what's the change in shear over the first 4 meters? It should be the area in the load curve for the first 4 meters, which is the area under this curve, which we already computed. Its base times height, it's 20. And the load is positive or negative? Negative. So 10 minus 20, hey, it's negative 10. That's great. We also know that the slope of the shear diagram is equal to the load. Well, what's the load when we start? It's 5, and it stays constant all the way through. So the slope is constant. And is the load positive or negative? Negative. So I get a negative slope. So there's my shear diagram for the first 4 meters. The change in shear from here to here is what? It's the area of the load curve. What's the load curve right here in this 1 meter zone? 0. So it's no change. Stays negative 10. And the slope of that curve is equal to the load. What's the load? 0. So here's a curve with 0 slope, horizontal line. So there's our next piece of the shear diagram. Now what happens is I go from the left side to the right side of this concentrated load. My shear changes exactly that amount. And the load is down, so it's negative. So 10 minus 8 is negative 18. The change in shear between these 2 points is the area in the load curve, which is 0, so no change. We match our minus 18 on the end. And of course, the slope of the shear diagram is the load, and the load is 0. So 0 slope, horizontal curve. So there's your shear diagram. Now, initially, it presents us with a little bit of a challenge, is that we now have a point where the shear, goes. Did I just kill my point of my pen? Oh, there it is. We go from positive to negative, so we pass through a 0 point here in shear. Where does that occur? Well, remember we talked about the similar triangles approach? This is a perfect one for it. So these are similar triangles. And this one has a height of 10, this one has a height of 10, so these bases must be the same. If they're the same and they add up to 4, they must be 2. So now I have all the pieces I need to draw the moment diagram. So I'll now assume a positive axis for moment. For x, positive axis for moment. All these values will be kilonewton meter. And let's put in what we know about bending moment. What's the bending moment at A? 0. What's the bending moment at B? 0. What's the bending moment at C? Minus 28. So I've got all my parts. So then it's just a matter of filling them in. Now my relationship for moment says that the change in moment between any 2 points is the corresponding area under the shear diagram. So looking at this region here, that's the change in moment I want to compute. What's the area of the shear diagram there? Well, that's easy. It's a triangle. 1/2 base times height. That's a value of 10. So I end up with a positive 10 because this is a positive area. 0 plus 10 is 10. And what's the shape of the curve? Remember, our relationship says that the slope of the moment diagram is equal to the shear. So what is the shear at A? It is positive 10. So I'm going to start off with a positive moment, positive shear, slope, sorry. And it's going to decrease to a value of 0. So this is 0 slope. This is a linear curve, so this should be a quadratic curve. So I'll draw a parabolic shape in there. Now the change in moment from 2 to 4 meters, this region is the area of this part of the curve. I'll distinguish that with a little finer hatching. What's the area of that curve? Well, it's a triangle. 1/2 base times height. So that's minus 10. 10 minus 10 is 0. All right. And what is the slope of the moment diagram? It's the shear. What's the shear value here? 0. 0 slope. It increases negatively to a value of negative 10. So connect those dots and you get a nice parabolic curve. So we now have a nice parabolic area. Now, over the next 1 meter, the change in moment is the area of this part of the shear diagram. What's that? It's minus 10 for the height and 1, so that's an additional minus 10. So what is 0 minus 10? Minus 10. I got to try to get this. My scale's going to be all out of whack. Because you can see I drew this as 10 and I drew this as 28. So, you're going to give me the ability to let that slide?
Only if we get it on the test.
You won't get it on the test. So minus 10, and the slope here should be equal to minus 10. Now this is also minus 10 slope, so really the slope should come down here. But I can't draw it like that. I've just run out of room. So even though it's like that for the drawing, these two slopes should be identical. They're both minus 10, and it stays minus 10. So now the change in moment here is equal to this part of the shear diagram, and I'll hatch that in so you can see that part. And what's that area? Well, base times height, 1 times minus 18 is minus 18. Negative 10 minus 18 is 28. And the slope should be the value of the shear, and the shear is constant, so constant slope of 18. Now this is a little bit better. You do see the slope get steeper as you hit the next section. So I really should have drawn this if I'd drawn it to scale, it would look a little nicer. But then there you are. So I like that problem. That's a good problem. Don't you like that problem? I like that problem. All right, any questions?